So the next section in integration is called partial fractions, and this is the same basic principle as with the trig identities section. There's no new special integrating technique. What we're doing is we're taking some maths we already know from earlier in the course and applying it to simplify an expression. We begin with something that we can't integrate, but we then apply partial fractions to it and turn it into a simpler expression which we can integrate, and that's it. So what we want to do is we want to start by saying, well, I've got 1 over x squared plus 2x minus 3. If I want to deal with this in terms of partial fractions, it will be helpful to factorize the denominator. It factorizes fairly easily into x plus 3 and x minus 1. Hopefully you can spot that. And what that means is that this can be rewritten as a over x plus 3 plus b over x minus 1. And then we just run through our normal partial fractions process. So what this means is 1 over x plus 3 times by x minus 1 is equal to a lots of x minus 1 plus b lots of x plus 3 over our x plus 3 times by x minus 1 denominator. And we can therefore equate the numerators. And there are a few different techniques. We can expand and compare coefficients. In this case, it looks like it's definitely going to be simpler just to choose an x value which zeros everything. So if I say x equals 1, then this bracket with the a becomes 0. So this tells us that 1 equals, because we're equating the numerators, 0 plus b lots of x is 1. So it's 1 plus 4, no, 1 plus 3, obviously. I'm jumping ahead of the game. So 1 is 4 lots of b, so b is 1/4. And then to do the same thing to find b, we can either substitute a quarter in here, but actually that's going to leave us with some fractions and is a bit awkward, certainly harder than using x's minus 3 and substituting that in, and that gives us that 1 equals negative 3 take away 1 is negative 4a. So we have b is 1/4 and a is negative 1/4. Now I can go back to this original expression and I can pop all that information in. So now I know that my 1 over x plus 3 x minus 1 is equal to negative 1 over 4 x plus 3, because it's a is negative 1/4, plus 1 over 4 lots of x minus 1. Those are our a and b. And now we're ready to integrate, because if I want to integrate this expression on the left, that's the same as integrating the expression on the right. So what we now have is that the integral of 1 over, and it was x squared plus 2x minus 3, is the integral of negative 1 over 4 x plus 3 plus 1 over 4 x minus 1. At this point you kind of have some choices. You could notice that I've got a common factor of 1/4, and you could pull that out and integrate 1 over x plus 3 and 1 over x minus 1, or you can just integrate this as is, because it's not that hard to do. So if I'm going to integrate this, then it's a reverse chain rule one. This looks a little bit like 1 over x, but we've got a coefficient, and this is x plus 3 instead of x. So we have to multiply it by the derivative of this, which is just 1, so it doesn't really make a lot of difference to what we're doing. So this is going to end up being negative 1/4, that's our coefficient, multiplied by natural log of x plus 3. And then I'm going to add 1/4 of natural log of x minus 1, and that's it. It's a pretty straightforward integration. I need my constant there as well. I could stop here, but I don't want to stop here, because I can tidy this up slightly, because I've got a coefficient of 1/4 on both of these, but this is a negative and this is a positive, and we know we have some rules of logs here. So that's going to be 1/4 of the natural log of x minus 1 divided by x plus 3. And that's just a slightly tidier final solution to this, one single natural log. And that's it. So we've used partial fractions to separate everything up, and then having it all separated up means it's actually really easy to integrate. And because of the way we deal with partial fractions, a significant number of the time that's going to be the end of it. Occasionally we'll end up with a quadratic or a cubic in some of the denominators, but we also have a strategy to deal with them because we've also shown how to integrate those earlier on in the chapter. So this is the summary that the textbook gives at the start of the chapter. Partial fractions can be used to integrate algebraic fractions. And that's really helpful information. It's just a reminder to us that these general tools that we have in algebra and across a range of other topic areas can be used to rearrange, simplify, and express things in a different way. And that rearrangement may well make the integration more straightforward to do, similar to what we were doing in the trig identities section. I'm going to go through one more example. And this additional example, there's a couple of things here. First of all, it's a more complicated partial fraction. But second of all, it's a definite integral. And when you see a definite integral, you may well be tempted to reach for your calculator. I'm going to just show you really quickly that you absolutely can do that, but there is a slight problem with reaching for your calculator. So if I type in x plus 1 and x cubed plus 2 x squared, and then I want to integrate it between 1 and 2, and I hit equals, and it does the integration absolutely fine, no problem with that, and it gives me 0.351 and so on. The problem is the question says in exact form, and for some integrals it will happily deal with this and give it an exact form, but for a significant number of the trig ones, of the ones that end up with natural logs in, they don't give you exact versions on the calculator because the calculator is doing some numerical approximations. And if it's a simple expression as the final answer, it will probably manage it. But if it's a complicated expression with multiple different terms in, if it's got some trig as well as some natural logs, if it's got natural logs as well as not natural log bits, it is unlikely to land on the exact form version of the answer. This is useful for confirming your answer at the end of the process. So I can get my final answer, and we'll do that, and then I can go back to my calculator and I can double check, is that 0.351? And if it is, I'm definitely fine, I've done it right. But if it says exact form in the question, it is unlikely to be doable on a calculator. So we need to sort this out. I have x plus 1 over x cubed plus 2x squared. Step number 1 is I need to factorize the denominator. Now, this time it's not a quadratic, it's not going to go to 2 brackets, but I can see that it has an x squared in both terms, and then x plus 2. And actually that's sufficient for dealing with it in partial fractions. I have a repeated root here, x squared comes up twice, and then I have my x plus 2, a repeated factor, sorry. And what that means is I can write it as a over b over and c over, because we've got a cubic, we're going to have 3 terms. The c over is x plus 2, and that's easy. We need to remind ourselves that when we have a repeated factor, then we end up with it repeated and it on its own in our partial fractions version. So I have a over x squared, b over x, and c over x plus 2. And my numerator is x plus 1. I did the whole thing in full last time, showing you the denominators matching up, but actually, hopefully, we know we don't need to really record the denominator. If we are careful with what we're doing, we can say, oh, well, my numerators must match, so x plus 1 must equal, and then a over x squared needs to be multiplied by x plus 2 to get it right. B over x needs to be multiplied by x and x plus 2, and c needs to be multiplied by x squared. And now I can begin my work of sorting all of this out. Obviously I can't zero the c term, because if I zero this, I also zero the b term, and I end up with no. So there's a couple of things I can do really simply. I can zero the a term by saying, well, what if x equals -2? Well, that tells us then -2 plus 1 is -1 equals, this term is now 0, and this term is now 0, so I just have cx squared. -2 squared is 4, so I've got 4c. So c is -1/4. I can also say what happens when x equals 0, because that will zero the b and the c terms. So then I have 1 equals 2a. So a is a half. And now I can't use this technique because we have this repeated root. I can't use this technique to find b, because zeroing either of these will get rid of b as well. So I need to pick another value, but I found out what a and c are. So if I pick something like 1, and we can pick any value we like here, so it's kind of up to you. But if I pick 1, because 1 is nice and easy to work with, 2 equals 3a plus 1 times 2 times 3, sorry, so 3b plus c. And then we can do a little bit of work here. A is a half, so let's make a little bit more room here. 2 equals 3 over 2, 3 halves, plus 3b minus 1/4. So 3b must be equal to 2 take away 3 over 2 plus 1/4. You can always use a calculator to double check these if you want to, because it's there, and it's always worth doing that little extra bit of checking on your calculator, because it doesn't take very long to do. And this is going to give us that b equals 3/4 divided by 3, which is going to be 1/4. So I've got my a, b, and my c, 1/4, 1/2, 1/4, and -1/4. So let's just rewrite this whole thing out again. So I have x plus 1 over x cubed plus 2x squared, and that equals a is a half, so 1 over 2x squared. B is a quarter, so that is 1 over 4x. And c is -1/4, so that's minus 1 over 4 lots of x plus 2. And now I'm ready to integrate. So the integral between 1 and 2 of my original is equal to the integral between 1 and 2 of my new thing, which is 1 over 2x squared plus 1 over 4x minus 1 over 4 lots of x plus 2. And just going to get ready for a minute. And we can see from here that I have 2 terms here which will give us the natural logs like we saw in that first example, but this one, 1 over 2x squared, will not. This is actually just a standard polynomial. It's easy to integrate because this is 1/2 of x to the minus 2. So this is going to give us, between 1 and 2, if I've got x to the minus 2, I'm integrating, so I'm going to raise the power, divide by the new power. So this is going to be half of x to the minus 1 divided by minus 1. We'll tidy that up in a minute. The second term is going to be 1/4 of the natural log of x. And the third term is going to be minus 1/4 of the natural log of x plus 2 between 1 and 2. No constant because it's a definite integral. So I can do a little bit of tidying up in here, which is quite useful. What we've got is a half of x to the minus 1 divided by minus 1 changes the sign. So this is negative. And then this is 1 over 2x to the minus 1. So it's 1 over 2x. And then I've got 2 natural logs with a coefficient of 1/4. One's add and one's minus, so I can combine them. And we're now ready to do our substituting in. Substitute in 2 and substitute in 1 and subtract them. So again, this is all relatively straightforward stuff. So this is negative 1 over 4 plus a quarter of the natural log of 2 divided by 4, so that's a half. Take away, and then if I'm substituting 1 in, that actually ends up being plus 1/2, and then take away 1/4 of the natural log of 1 over 3. Again, I can do a little bit more tidying up. Negative 1/4 plus a half is going to be 1/4, and then I've got plus 1/4 of the natural log of, I'm subtracting again, so it's a half divided by a third. I'm going to do one final little bit of tidying up from here because I've got a factor of a quarter in both of these, so I can just pull that out, which is 1 plus natural log, and then a half divided by a third is 3 over 2. And actually I can kill my absolute signs, which I needed when I had my x terms in, because I now have numbers which are definitely not negative. So ln of 3 over 2 is absolutely fine. And this is our final exact answer. And then we need to just remind ourselves we had an answer on the calculator of 0.351, so on. It's worth just going back here and double checking that they match. So what is 1/4? Ooh. 1/4 multiplied by 1 plus the natural log of 3 over 2. And lo and behold, it's the same thing. And that's really helpful because that tells us that we've done everything right and we've landed on the correct exact value. We've not made any little mistakes, which is very easy to do in a question as large as this. So what we've seen is partial fractions, the straightforward versions, and also the versions with the repeated factors. If you're good at them, you can sort these integration questions out. There'll be a couple of other videos walking through example 20 and 21 from the textbook, but it's very similar content, so it's up to you whether you want to watch them or not, depending on whether you can follow the information in the textbook on those two examples.